Okay, so all this fun with modulo has been specifically to look at RSA encryption. And so I just love it. I love the fact, okay, so RSA encryption is really cool because apparently the US government had been using it secretly for a really long time. And I should really research these better before I start these videos, but you know, whatever, you can Google stuff. RSA encryption was used by the US government to do like all kinds of cool stuff, like at least since the 60s or 70s or something like that. And it was like this super big secret. And then some like dudes were just like, hey, it was like the late 90s, I think. And they were like, hey, we came up with this really cool encryption algorithm. And the government was like, oh no, you just like completely outed us. So this had been developed a lot earlier. I think it was named after the people who came up with it publicly, but I'm not 100% sure. Anyway, that's something for you to figure out. But this is how you can do encryption with with a public key. So okay, let me explain why encryption is normally kind of dumb. So like maybe you've heard of the Caesar cipher where you have A, B, C, D, E, F, etc. And the numbers are 1, 2, 3, 4, 5, 6. Now the only way if I wanted to, you know, send you a secret message, I would send you 3, 2, 1. Now in order for you to decode the message, you would say, oh, say 3 is this and 2 is Kuba. I don't know why I just sent you that message. That was a stupid message. But the thing is, in order for me to do this with you, both of us have to have a copy of this. So like if I'm a website and I have like 1 million customers, I would have to have 1 million of these. And then every time I had a new customer, I'd have to generate a whole other set of this. So it's like if you want to send me a secret message, first of all, I have to send you the key. And how do I send you the key secretly without anyone else finding it? So it's really dumb. So basically what they came up with is the idea that what I can do is I can give you this public key to decrypt. It's not this. I can give you a public key to encrypt something to send it to me. But then once you send it to me, even you can't unencrypt it. You can't decrypt it. So what's kind of cool is like I'll give you this method to encrypt something and you encrypt it as like 725. And then you're like, wait, what did 725 mean? You actually don't have the equipment to decrypt that. I have a private info, and only my private info can turn the 725 into, you know, kisses or whatever I was trying to say. You know, if you try to decrypt it, it's just going to say sad face because it can't do it. So that's what's really neat about RSA is as a public key. So anybody can send me secret messages. But even after you encrypt your own secret message to me, if you forget what it was, you can't see it. You can't unencrypt it. There's just no way to do it. Okay, so here's the setup for RSA encryption. Is you're going to start off by choosing 2 distinct primes, so P and Q. We've played around with prime numbers in our modulo theorems. You're going to find what they're multiples of, calculate this other thing phi, find a random E that's between 1 and phi, meeting some requirements, and then you're going to find D. So this is just the setup, is finding all these pieces. Okay, then if you actually want to play, the 3 of the things that you had calculated would be E and N, and then you're going to keep D secret. Okay, so if you look at this, the only way to figure out what D is, okay, the way to figure out what D is you got to look at what went into D. Okay, E and N. So in order to do N, you'd have to know what P and Q are, and P and Q are prime. So that's really why this ends up being super, super, super fancy, is because if I pick giant prime numbers, okay, so like if I say 21, you can be like, oh, your prime numbers are 3 and 7. But if I pick like 2 ginormous, you know, prime numbers and I multiply them together and I get 5, 71, 8, 30, 3, 12, 14, 7, 9, 1, I don't know if that's actually prime, then you'd like have to think about it and be like, what is the co-prime, what is the prime factorization of those 2 numbers like that? You'd literally have to go through all of them. So if you're doing this with 2 prime numbers that are originally like 1,000,000 digits and 1,000,000 digits, then you get a gajillion digit D, and or gajillion digit n, and then nobody can bust up your algorithm. So you can't work backwards very easily. The better your prime number generators are, the more secure your encryption is. It's super cool. I like it. So if you actually want to send a message, so if you want to send a message to me, M, now, okay, if the message is M, this is kind of a big deal. M, this only works if M is less than the minimum of P and Q. So obviously anything I'm doing by hand, you know, there's not a really long message. But if you've got gigantic prime numbers, this shouldn't come up as being an issue. There's a whole lot of theory to why this isn't a big deal. It's a big deal if I'm trying to do a small example to show y'all, but it's not a big deal in real life because these prime numbers are so big. So to send a message to me, you're going to encrypt with my public keys. So I've made E and N public. So if you want to send me secretly the message M, you go M to the E, you mod N it, and then you get this encrypted message C. Okay, so this is the secret code. And so you send me like, hey, dude, guess what? C. And I'm like, awesome. And then I'm going to decrypt your secret message. I need my private information. So I kept D private, right? So D was like kind of super secret, my super secret D. What I'm going to do is I'm going to take your C, I'm going to raise it to the D power mod M. No, not mod M, mod N, which I also know. It's public, but I also know it. And that is going to give me back M. So I can get the M out by going C to the D and mod N. So if you don't know my D, you can't decrypt it, okay? Not even the original sender can decrypt it. And so then, you know, if you and I were going to play, you know, we would each have our own set of public and private keys, and we could go back and forth and send messages back and forth. So when you send stuff to me, once you encrypt it, you can't read it. When I send stuff to you, once I encrypt it, I can't read it. And that's how it works, is you just send these back and forth and back and forth and back and forth. It's super cool. So let me show you an example of how this works. Let's see. Okay, so let's say that I've done this where I have two distinct primes, P and Q. So without too much effort, I can say, awesome. So N is going to be equal to, what, 11 times 13. So that's what, 43. Okay, and then phi is going to be equal to each one of those minus 1. So 10 times 12, so phi is equal to 120. Now it says choose E such that E is between that and their coprime. I just honestly started at 2, and then I looked at 3, and then I looked at 4, and I just kept going up till I found the smallest one. So I just did this by hand. I picked E equals 7 for no particular reason, just because I wanna. There are probably plenty of other E's that I could have picked. I just picked that one. Well, yeah, because any prime number, pretty much, lots of prime numbers would meet that requirement. Like 11 would be coprime with phi, or 41, I guess, would be coprime. But I'm just picking E because I'm lazy. All right, now this last one says find D where E times D is congruent to 1 mod phi. I will admit I kind of gave up trying to do that by hand. I was starting to check them one by one. I'm like, this is going to take forever. I ended up making a little script in MATLAB to do it, and I got a D equal to 103. So if you want to check it, you can. E times D is 7 times 103. The question is that congruent to 1 mod 120? Oops, mod 120. So 7 times 103 divided by 120 is going to give me 6.083. Remember, I'm going to subtract off the 6 and multiply by 120, and I'm going to get 1. So yes, that's correct. All right, so I have these. Now I am going to go take out a billboard. I don't know what this is, a billboard. And I'm going to say, you know, PM me. And that E is equal to 7 and D is equal to 103. And anyone, no, I would not say that. I would say E is equal to 7 and N is equal to 143. Yikes. And anyone who is super cool enough to know what that means would be like, awesome, I'm going to send you a secret message. All right, so I have like my little friend over here, my new friend, and they want to send me the message 3. Okay. So they're going to get on their little typey. This is a apparently supposed to be a desk. I don't know what I'm doing. And what they're going to do here is they're going to go, remember, it's m to the e mod n. M to the e mod n. So they're going to come over here and they're going to say 3 to the 7 mod 143. Okay, so 3 to the 7 divided by 143. And so I'm going to subtract 15 off of that and times it by 143 to get the remainder. So the remainder is 42. I didn't do that on purpose, but I think it's funny that that's how it turned out to be. So their secret answer is 42. And so they can take a billboard and they want to send me a secret message, or they have a slightly different color. They're going to use green. They're going to make a green billboard. And they're going to tell me, hey, 42. I'm going to be like, awesome. And so then I'm going to go to like my house after I see this billboard and I'm like, yay, somebody wants to hang out with me. I'm going to go into my little house and I'm going to go into the basement and then I'm going to go into the secret room behind the basement. And from here, I'm going to go find the D is equal to 103, which I've been keeping very, very, very private to me. All right, so if I want to decrypt their message, again, this is in this room, I'm going to go 42 to the 103 mod 143. And if I did this on my calculator at first, if I try to do 42 to 103 divided by 143, I can't even see what the stupid first part of it is. I can't like just subtract off the floor and then multiply the remainder. I just can't see it. It's not there. But if I play around in my calculator, I actually find a remainder function. So I can do remainder of 42 to the 103 mod 143 and get an answer, and the answer is 3, and I'm like, yay, somebody loves me. Okay, so that's how that works, is I can publish this, and they can publish this 42, and literally nobody knows, you know, what that means. So if later on this person is like, oh, wow, that was a bad decision text, I don't know what that even meant, what did I even say, they can't figure it out. So if they were making bad choices and they sent me a secret message and they forgot what it was, now they can't decrypt it. They're just too bad. What's funny though is I like to show this as well. If I try to put mod 104 to 42 to 103 mod 143 into MATLAB, it comes back with 13, which is clearly not equal to 3. And that's because I guess whatever version of MATLAB I have is not as powerful as whatever operating system I have on my TI-89 emulator here. And I love my TI-89. It's just absolutely amazing. So we actually, if you want to do this in MATLAB, and other programming languages would have different levels at which they're going to be effective in doing this kind of stuff. So I always like when I'm running code, so I wrote an RSA algorithm to play around with, and when I originally did it, I ended up getting 13 back, and I'm like, that doesn't make any sense. I kind of had to do it by hand. Then I did some research and found out that this is a known issue with MATLAB, that there is a limitation on how effective the modulo function is. So that's, again, why we want to play around with all of this, and it's pretty neat. Anyway, I do eventually want to do a video on how to prove RSA encryption, but I thought for a first step, at least show you how it works.